Let's look at simplifying some trig expressions involving double angle identities. For our first example, we want to take the quantity sine of theta minus cosine of theta all squared. So when we see something being squared, that means we're multiplying it by itself. So I have the sine of theta minus cosine of theta times the sine of theta minus cosine of theta. So to multiply this out, we need to FOIL. So when we do our first terms, we're going to have sine times sine, and that's going to give me sine squared of theta. When we do the outside, that's a sine and a negative cosine. So we're going to have a negative sine of theta times cosine theta. For the inside terms, we have a negative cosine and a sine. So we're going to have minus a cosine theta times a sine of theta. And for the last terms, we're going to have a negative cosine times a negative cosine, and that's going to become a plus cosine squared theta. If we look at the two middle terms, one is a sine theta cosine theta, and the other flips that around and says cosine theta sine theta. It doesn't actually matter the order of multiplication, so I can rewrite those so they're the same order. So that would give me the sine squared theta minus the sine theta times the cosine of theta minus the sine theta times cosine theta plus the cosine squared of theta. And so those middle two terms, they're actually identical, so they're like terms, and we can add them together. And so I have the sine squared theta minus 2 sine theta cosine theta, and then plus cosine squared theta. All right, to finish simplifying this problem, note that we have a sine squared theta plus a cosine squared theta, and that's our Pythagorean identity. And so I know sine squared plus cosine squared is equal to 1. And so that leaves me with 1 minus 2 sine of theta cosine theta. And I also recognize 2 sine theta cosine theta is our double angle identity for sine. So I can rewrite this as 1 minus the sine of 2 theta. And that would be as simplified as I can get. All right, for our next problem, we have the cosine of 2x divided by the quantity sine x times cosine x. And we want to simplify that. So right off the bat, again, we see the cosine of 2x, and so that should indicate that we need to do a double angle identity. Okay, so the difficulty with cosine is that it has 3 ways of writing it. So we could write the cosine of 2x. We could write that as 2 times the cosine squared of x minus 1, or we could write it as 1 minus 2 sine squared of x, or we could write it as the cosine squared x minus the sine squared x. So all 3 of these are just related by the Pythagorean theorem. Okay, so we can get from one to the other 2 just by using the Pythagorean theorem. So it's not like it's that big of a problem, but which one we pick can sometimes make a difference on how easy it is to simplify. As I take a look at the original problem, notice we have a sine x and a cosine x in the denominator. So I'm thinking let's use the identity that has both a sine and a cosine in it. So I'm going to rewrite the cosine of 2x as the cosine squared x minus the sine squared x all over a sine x and a cosine x. So as I look at that, I can't cancel anything right now because in the numerator I have a subtraction, so I can't reduce anything there. So is there anything that we can do? We could factor. We could also break the fraction apart, right? So we have a common denominator, and we're having 2 terms in the numerator. So let's break those 2 terms apart across that subtraction. So that means we're going to have the cosine squared x over a sine x cosine x minus the sine squared x over the same denominator, a sine x and a cosine x. In our first fraction here, we can reduce the cosine squared with the cosine. So the squared is going to go away, and it's going to cancel with the cosine in the denominator. And so we're going to be left with a cosine x over sine x. In the second fraction, basically the same thing's going to happen, but we're going to lose the sine squared is going to reduce with the sine in the denominator. And so we're going to be left with a sine over cosine. So we have the cosine of x over sine x minus sine x over cosine x. And we could just do one more step here. I know that cosine x over sine x is cotangent x, and I know sine over cosine is tangent x. So I've been able to rewrite the cosine of 2x divided by the quantity sine x cosine x as the cotangent of x minus the tangent of x. All right, let's look at one more example. We did one similar to this in a previous lesson. We're given that sine of phi is equal to a negative 4/5, and phi is in the fourth quadrant. We want to determine the value of the sine of 2 phi, the cosine of 2 phi, and the tangent of 2 phi. So let's go ahead and write out what our identities are going to look like. So sine of 2 phi is 2 times the sine of phi times the cosine of phi. So to do that, I need sine of phi, which I already know, and I also need cosine of phi. For cosine of 2 phi, again, this one has different ways to write it. Since I already actually know what sine is, let's write it in terms of just sine. So I know cosine of 2 phi is equal to 1 minus 2 sine squared of phi. So I don't even need to do any work for that one. I already know what the sine value is, and so I can go ahead and compute that. For the last one, tangent of 2 phi, we need to compute the 2 times the tangent of phi divided by 1 minus the tangent squared of phi. So in order to compute these three values, I need sine, which I already have, I need cosine, and I need tangent. Now, we could do the same thing we did before. We could use the Pythagorean theorem to figure out cosine, and then we know tangents, sine over cosine. So I could totally do that. But let's try it a little differently just to illustrate another way that we could go about figuring out these values. So since I'm told that sine of phi is a negative 4/5, and I know that that's in the fourth quadrant, let me draw an xy axis, and let me draw a right triangle extending outwards, so the hypotenuse extends outwards from the origin, and then we draw a vertical line from the end of that line back to the x-axis, and so that's going to create a right triangle. And phi is going to be the angle, the acute angle next to the origin. So we have this right triangle. The hypotenuse comes straight out of the origin from angle phi. The opposite side is the vertical side, and the adjacent side is along the x-axis. Now, if sine is a negative 4/5, that means that the opposite side has to be 4, and the hypotenuse has to be a 5. And if we think about that negative 4 telling us that 4/5 telling us part of the coordinate for the point on the end of that triangle, then we might think of that as being a negative 4. Okay, so by putting that negative there, it's just going to take care of the signs, whether our results are going to be positive or negative. So the other piece that we need to find cosine and tangent is we need the adjacent side. So we need side A, for example. So that means we could use Pythagorean theorem. So a squared plus a negative 4 squared must equal a 5 squared. So we have a squared plus 16 is equal to 25. we subtract the 16 from both sides, and we get a squared is equal to 9. And so a is going to equal a positive or negative 3. Now, just like we did with that 4, because it's going downwards from the x-axis, I labeled it as a negative 4. The a value is the x value going to the right. So it's actually going to be a positive 3. So we think of that as being a positive 3. So from here, we can figure out that the cosine of phi is going to be a positive 3/5, which should make sense because we're told phi is in the fourth quadrant. And we could say that tangent of phi is going to be a negative 4/3. And again, it's negative because it's in the fourth quadrant, but that's also based off the negative 4 that I was using. All right, so all that's left is to compute what our values were, taking what we just got off that right triangle. So the sine of 2 theta is equal to 2 sine theta, or sorry, phi, 2 sine phi cosine phi. And so that's going to equal 2 times a negative 4/5 times a 3/5. And we multiply that. Remember, the 2 is technically over 1. So if we multiply all the things in the numerator, we have a 2 times a 4 times a 3. So that's going to be 2 times 4 is an 8, and 8 times 3 is a 24. So we have 24 in the numerator. The fraction is negative because we have one negative. And in the denominator, I have a 1 and a 5 and a 5. So that's going to be 25. So the sine of 2 phi is going to be a negative 24 over 25. For the second part, cosine of 2 phi, we have 1 minus 2 sine squared of phi. So I'm going to replace the sine with that negative 4/5. So 1 minus 2 times a negative 4/5 squared. If we square that negative 4/5, we're going to have 1 minus 2 times 16/25. 2 times 16/25 is going to be 32. So we're going to have 1 minus 32/25. And to simplify that, rewrite the 1 as a 25/25 minus a 32/25. And 25 minus 32 is going to be a negative 7. So negative 7 over 25. All right, last part here, 2 tangent of phi over 1 minus tangent squared of phi. That should equal tangent of 2 phi. And we now know what the tangent of phi is. It's a negative 4/3. So we're going to have 2 times a negative 4/3 divided by 1 minus a negative 4/3 squared. And so if we simplify that a little bit, 2 times a negative 4/3 is going to be a negative 8/3. And that's going to be divided by 1 minus a 16 over 9. And if we use a common denominator, 1 minus 16 over 9 would really be 9/9 minus 16/9. And so 9 minus 16 is going to be a negative 7. So we have a negative 7/9. So we have the fraction negative 8/3 over negative 7/9. And then we can flip and multiply. So we have a negative 8/3 times a negative 9/7. For our fraction here, the 8/3, the 3, is going to reduce partially with the 9 and the 9/7. So the 3 will become a 1. The 9 is going to become a 3. And so I'm taking a negative times a negative, which becomes a positive. I'm taking an 8 times a 3, which is a 24, and a 1 times a 7, which is a 7. So the tangent of 2 phi is going to be a positive 24/7.